Hi everyone, my name is Hsiung. Today I'm going to share our work towards compositional adversarial robustness, generalizing adversarial training to composite semantic perturbations. This is a joint work with National Chen University, Columbia University, IBM Research, and the Chinese University of Hong Kong. Compared to traditional perturbations bounded in LP ball, semantic perturbations are more realistic and easily to generate. However, we found that most models are vulnerable to this kind of perturbations. Despite a robust model designed for LP norm perturbations, we can still see that it is not stable enough to provide consistent and correct predictions. We propose a new defense algorithm, Generalized Adversarial Training, GAT, to counter this threat. In this example, no matter how we change the perturbation level, the GAT model will not be affected and remain correct. In the past, most research is trying to explore perturbations in LP ball. That is, they would try to add some spatial design perturbation on the image and make them imperceptible to human. But the machine learning models will be affected, and this vulnerability is what researchers want to address. But considering only one perturbation is not enough, as we have observed that modern robust models are susceptible to semantic perturbations, as well as the composite perturbations. Therefore, we propose composite adversarial attacks, CAA, to generate hardened adversarial examples and generalized adversarial training, GAT, to obtain a robust model against them. The first part of our methodology is composite adversarial attack. Given an input image X and the attack space A1 to AN, CAA could generate the composite perturbation for it. First, since we have multiple attack components in each attack space, CA will optimize the attack order, and when the order is determined, CA would optimize each attack component. The attack order is optimizing through a scheduling matrix Z, which could be considered as an n by n doubly stochastic matrix. And each row of Z, Z1 to Zn, represents the possibility of each attack to be chosen at each attack step. So the order optimization is to optimize the scheduling matrix Z. To this end, we generate a surrogate image X0 by weighting each type of attack perturbation with its corresponding possibility at each iteration. We then use this surrogate image to compute the loss and update the scheduling matrix. Since each semantic attack has its own perturbation value, for example, the perturbation interval of Hsiung is ranged from -pi to pi. So given the attack sequence, we then utilize the projected gradient descent to optimize each attack component with this formula, searching for the best perturbation value. This is an example showing that how the attack order affects the attack success rate. The image below the perturbation block contains all perturbation before it. For example, the first image only contains a Hsiung perturbation, but the last image contains all the perturbations before it, including hue, saturation, rotation, brightness, contrast, and L-infinity perturbations. And the top one confidence score of each image is also shown below it. We could see that the attack order matters, because if we move the L-infinity perturbation to the first place, then this model would not be easily fooled. This also demonstrates that finding the attack order is important in generating composite perturbations. The second part of our method is to defend the composite perturbations. We generalize the standard adversarial training approach with our proposed CAA. We follow the min-max setting proposed by Madri et al. To design our objective function. The inner maximization is to generate composite adversarial examples, optimizing using CAA. And the outer minimization is for optimizing the model parameters theta f. For our experiments, We include a variety of baseline models in our setting. Each of them is considered as robust models. Our results on CVPR is very promising, as we could see that GAT outperform other baseline by a substantial margin, demonstrating that GAT could be robust to composite perturbations. We also show two order settings, random ordering and schedule ordering. And by using schedule ordering, the robust accuracy shows that it will significantly lower than random ordering, showing that our scheduling attack can further improve the attack success rate and lower the robust accuracy. Similarly, results on ImageNet also show that GAT model can achieve the highest robust accuracy. More experimental results can be found in our paper. When we visualize the model loss landscape over the semantic space, we found that GAT has a smoother, flatter, and lower loss curve compared to other models. This shows that our proposed GAT algorithm can indeed train models that are robust to composite adversarial perturbation. In our project page, we maintain a leaderboard to track the composite adversarial robustness progress. If you are interested in joining the leaderboard, please look for the instruction in our project page. In conclusion, we believe our work sheds new light on the frontiers of realistic adversarial attacks and defense. Our experimental results demonstrate that CA can easily crack more than robust models with the help of a novel attack scheduling design for multiple perturbation types and optimizations for each attack component. CA-generated adversarial examples can further enable GAT models to achieve state-of-the-art robustness against various adversarial perturbations. Thanks for watching. We will be presenting our papers on Thursday afternoon. Drop by our poster if you have any questions. Our models and code are available on GitHub. Please visit our project page for more details and demo.